Okay, exercise 1004 is about proof using vectors. Now this can be quite tricky, so I would like you to practice this quite a lot, and as well as doing 1004, I'm going to provide the exercise from the Cambridge textbook as well. Now the most important things here are you must always draw a diagram. If you don't draw a diagram, you're really going to struggle with these. That's really important. Sometimes your diagram might want to be on a Cartesian plane, okay, because the location of the origin can prove to be very, very useful. You might use sums of vectors, you might use differences of vectors, you might use dot products, particularly if it's talking about parallel, perpendicular, or angles between vectors, and you could potentially use vector projections as well. So here's my first example. So ABCD, I'll just mention here too, actually, when you have labelling of a quadrilateral here, ABCD is a quadrilateral, the labelling is cyclic, A, then B, then C, then D, and it is preferred it goes anti-clockwise. I can't promise you that everybody's going to stick to that, but that's what it's supposed to be. So I have stuck to that. Now it's got midpoints P, Q, R, and S as shown in the diagram. So there's P is the midpoint of AD, Q is the midpoint of AB, R is the midpoint of BC, and S is the midpoint of CD. Now, none of these are actually vectors at this point, but we can think of them as vectors. Now we have to prove that PQRS is a parallelogram, and it's definitely well worth doing that on something like GeoGebra. So GeoGebra, you can plot 4 points, join them up as a quadrilateral, you can find the midpoint and join them together. So that's the first thing I want to do here, is actually join those together. Here it actually looks like a perfect rectangle almost. It doesn't have to be a rectangle, that's just the way I've drawn my diagram. My original diagram looks a bit like a kite. So this comes out looking like a rectangle, but it doesn't have to be. It does have to be a parallelogram, and that's what we're going to prove. So first of all, let's look at the vector QR. So this vector right here. So the vector QR is that vector plus that vector going in those directions. So that's QB plus BR, just some vector addition there. Now, the interesting thing here is QB is half of AB. So let's write that down, and BR is half of BC. Now, from there, what I can do is I can factorise out the half, and so I get half of AB plus BC. Now, AB plus BC, they've got that common B in the middle, they can just dissolve, or AB plus BC is the vector AC. So that's half of AC. Now let's consider the vector PS, because if this is true, if this is a parallelogram, then QR and PS are going to be parallel and they're going to be the same length. So they're going to be equal vectors. If we can prove that they're equal vectors, that's all we need to do. If they're equal vectors, it must be a parallelogram. So PS in the same way is PD plus DS. Now PD is half of AD and DS is half of DC. Factorise out the half. The D does its magic disappearing act, so that's just AC. So half of AC, missed my arrow on AC, that's all right, which is equal to QR. So those two are equal vectors. If they're equal, they have the same magnitude in the same direction, so therefore they are parallel. We could similarly show that PQ is equal to SR, that they're both equal to half of DB. We don't need to do that for this proof. Being parallel, having the same direction and the same length is sufficient to prove it's a parallelogram. So because PS, the vector PS, is equal to the vector QR, they've got the same magnitude, they've got the same direction, therefore they're the opposite sides of a parallelogram. So that's our proof done. Okay, I'm going to do example 9 from the textbook. I think the textbook really overcomplicates it. And they've actually got a little bit of a mistake in it as well that I'm going to show you. So it says given OA is the vector A0 and OB is the vector 0B, and vector AO is equal to vector AC. Now, the mistake in the textbook is that it doesn't have these as vectors, but they actually do need to be vectors. So I'll just prove that to you briefly. So let's just draw a little diagram of it. So it's a little bit rough. I'll just make that a bit nicer. There we go. Okay, so the vector OA is A0. So that's that vector there. So the point A would be there. And the vector OB, 0B, so up there. So that's the point B there. Those are vectors. And then it said that AO equals OC without writing them as vectors. So technically speaking, C could be down here somewhere if that was right. As long as this length equals that length. And then it said to prove that that's an isosceles triangle. All right, triangle ABC is isosceles. Now, you can see in that diagram that clearly it's not, with AB equals CB. Clearly this line and this line are not the same length. You can see that's really obvious. So these must be vectors or this just doesn't work. Okay, so let's have a go at proving this. So the first thing, of course, we want is a diagram. Now, because the origin is basically identified with these zeros, it is really useful to have this diagram on a Cartesian plane. So there we go. I've sketched the location of A and the location of B based on those vectors, treating them as radius vectors. Now, the first thing we want to look at is where is C? Now, because AO, that vector, is equal to OC, we know that C goes over there. And we can write it in this column matrix form as well. So because AO is equal to AO, OC is equal to then, because AO equals OC, OC is equal to the negative of OA. So see, that was AO there. This is the negative of OA. It's been reversed. So that's the negative of that. So just negative A0. So that gives some coordinates basically for C, which makes it really, really easy to solve. So if you get that diagram right, you're almost there. So the vector AB, from A to B, is going to be OB minus OA, just from vector subtraction. And I've just put in these matrices as we were given them. So subtracting that, so 0 minus AB minus 0, so that's negative AB. So the magnitude of that vector is just a squared plus b squared, magnitude squared, sorry. So a squared plus b squared. Now, also looking at the vector CB, it's OB minus OC. And putting in those coordinates as we know them, equals AB. So let's find the magnitude of that one as well. And that again is a squared plus b squared. So those magnitudes are equal. So I've actually proven that the magnitude of AB equals the magnitude of CB. That's what that says there. Those are not vectors. Those are lengths, basically. They're magnitudes. So because of that, it is isosceles. Two sides have the same length, AB equal to CB. Now we also have to prove that angle ACB, so this angle, is equal to angle CAB, that angle there. Now we know that's true because they're the base angles of an isosceles triangle, but they've asked us to prove it. Okay, we do know it's true though. So if we're finding angles, then you do need to start thinking dot products. So let's look at the dot product of CB with CO. Now notice both of those start with C. So CB, CO, we're going to calculate that. So just using the simple dot product rules again. So A times A and B times 0. So that's just A squared. Now we also want to look at the dot product of AB times A0. Now notice they both start with A's to be consistent with these. So we've got the dot product of AB with A0, and that's concentrating on that angle there. So if I go from CB to C0, I need to go from AB to A0 or AO to be consistent. So let's find that dot product. Negative a times negative a is a squared, plus 0 times b. So those dot products are equal. That's really important. The dot products are equal. Still not quite enough to tell us that the angles are equal, but let's do a bit more. So we know the magnitude of CB is equal to the magnitude of AB, and that was from part A. So we know that CO is equal to OA. We said that up here. Okay, that was given originally. So therefore we know that the magnitude of CO equals the magnitude of OA, which that doesn't matter which way round it's written, that's also equal to the magnitude of AO, because that's a magnitude doesn't have direction. It's a scalar, not a vector. So let's look at that dot product of CB times CO using the formula with the cosine in it. So it's the magnitude of CB times the magnitude of CO times the cosine of the angle between them. Now, interestingly though, we just said up here that the magnitude of CB is equal to the magnitude of AB. Also, the magnitude of CO is equal to the magnitude of AO. So that's really useful. Now let's look at the dot product of AB with AO. So we're just looking at these same two formulas again. And we know these two things are equal, we proved them over there. So just using the formula, the magnitude of AB times the magnitude of AO times cos of the angle between them. Now the interesting thing here is we know from our diagram that both those angles are acute. That's quite important. So these things, that one and that one, are equal to each other. We know that from over here. And because these angles are both acute, so just dividing each side by those two things, cos alpha equals cos theta. They're both acute angles, which means that alpha has to equal theta. So therefore those angles are equal. I do think it's worth looking through the examples that they've got in the textbook. I also think it's worth looking at the examples that Cambridge has provided in the exercise 8D, which I have provided here. It's an excellent resource. I definitely advise doing that textbook exercise as well. So there are their examples, they're all there, and there's the exercise. I will need to get you the answers. I haven't put those on here yet, but I will add those as well to the bottom before I upload this.